My name is Jason Tranquita. I am a senior programmer at Volition. I've worked on rendering and tools primarily, most recently on Red Faction Guerrilla. Today we're going to be talking about using the GPU to do real-time texture compression for DXT1 or BC1 formatting. I'm going to talk a little bit about why we want to use the GPU. Then I will give everyone a little bit of a primer on the format of DXT1 just in case people don't know. And speak a little bit about how we do it, some tricks to make it work per platform. It actually varies a little bit per platform that we've worked on, and a few pointers on making it run fast. When I started putting together this presentation, I realized that I have a lot more than 25 minutes worth of stuff to talk about, so I'm going to be moving pretty quickly through things. I hope to have a little bit of time for questions at the end, but we'll see how that goes. I just want to cite some prior work before we start. A couple years ago, Intel and id published a paper, Real-Time DXT Compression is an excellent source of information. It focuses primarily on a CPU implementation of this, but this is the algorithm that my work is based on, as well as FastDXT, which is a very good implementation that you can download on the CPU and see what's going on. Okay, so the question is, why would you want to use the GPU to compress textures? A lot of games are having a lot more runtime generated content now, whether it's blending of maps, dynamic cube maps that you might be keeping around for more than one frame and you want to save some memory. There's a lot of user generated content. For Red Faction, what we wanted to do was we had a terrain texturing system that artists wanted, of course, unlimited layers of textures that they could blend together. And you can't write efficient shaders that are going to blend unlimited layers of textures. Well, instead of blending them all every frame, what we decided to do was we would blend the textures in the area near you, store that as you moved around, and compress it. The reason we decided to go with the GPU is first because doing it on the CPU was slower than using the GPU. And second, when you did the compression on the CPU, it required a certain amount of lag from when you wanted to generate your texture and when it was actually available. When you use the CPU to compress something that's been generated by the GPU, you have to wait until the CPU is done blending it. When the GPU is done blending it, you've got to then compress it and then wait, another couple frames until you can get it back to the GPU at times. It was sometimes 3 to 4 frames worth of lag, and that really wasn't acceptable for what we were doing. I was going to go up front a little bit about performance. CPU implementations, these numbers are from id's paper. They were getting around 180 megapixels a second on a single core, 750 megapixels a second on a quad core. These were 3 gigahertz Xenon. On the Xbox 360, we were able to get 1,800 megapixels per second, which equates to just a little bit over half a millisecond to compress a 1024 by 1024 texture. PS3 was a little bit slower. It was usually about 0.75 milliseconds to compress a 1024 by 1024 texture. Okay, so DXT is a block compressed format. It stores 4x4 grid of texels, and for every 4x4 grid of texels, you're storing 64 bits worth of data. The first 2 things that you store are 2 colors that represent endpoints on a color line. These are stored as 565 colors. And then you store 32 bits worth of indices. There's a 2-bit index for each texel, and those indexes select between the 2 colors that you've stored as well as 2 color values that are interpolated between those 2 stored colors. So the indices, index 0 is the first color that you've stored. Index 1 is the second color, very simple. Index 2 is a 2/3 blend between color 0 and 1/3 of color 1. And index 2 is a 1/3 blend of color 0 and 2/3 of color 1. So you can see with the 2 endpoints for 0 and 1, those are the interpolated colors we'd have available to us. One thing to note is DXT does support a 1-bit alpha mode. I'm not going to go too into depth into that, but if you use that mode, your index 3 is a 50% blend between color 0 and 1, and index 4 represents a transparent pixel. Okay, so the basic way that you're going to compress a DXT texture. You're going to get your 4x4 grid of source texels. You are going to find your 2 endpoints that you want to use and store. You will match each of the 4x4 texels to the best fitting color. You then have to create the binary representations of these, your 565 colors, your bit shifted indices and stuff like that. Now that's pretty much standard. You do the very similar things on CPU and GPU. On the GPU, you have another step of how are you going to get the results into a texture. You can't render directly to a DXT1 texture. No GPU supports quite doing that. So I'm going to jump ahead quickly to the last part, getting results, just so you have an idea of what we're doing. I'll reference this further later, but it varies per platform. I'll go into the platforms later. In general, what you're going to do is you're going to render to a texture that's 1/4 by 1/4 the resolution of your source. So for a 1024 by 1024 source, you're going to render to a 256 by 256 target. And that's because every target pixel represents a DXT block, and it'll be representing 16 of your source pixels. And if available, it's best to use a 16, 16, 16, 16 unsigned format. This works very well for DXT because the DXT block can be broken nicely into 4 16-bit values. Your two colors are each a 16-bit value, and then your indices, you can split them up into two groups. Okay, so how do you get your 4x4 grid of texels? This is, probably the simplest part. You're basically just sampling a 4x4 grid in your shader. The only real things that you'd want to note are that you want to use, in general, point sampling. You don't want to be getting blends between there unless you want to generate some bitmaps, and you can kind of get a free bitmap out of it if you want by changing some of the relative dimensions. When you sample, it's best if you can sample in the order that the indices will appear. It just makes the order that they will go into the indices. It makes it easier throughout the entire algorithm if you don't have to remap things later. And then on certain platforms, there are instructions available that make this a little bit cheaper. If you don't have to calculate UV offsets, you're saving yourself instructions. Xbox has texture fetch instructions that allow you to specify offset from a UV. Likewise, DirectX 10.1, I believe, has similar features. So the next step is finding your endpoint colors. This can be very expensive. This is where most offline compressors spend most of their time. Some of them will do brute force algorithms to try to find, out of the 16 source textures you have, texels that you have, which ones would be the best endpoints and test every possible combination. Typically, these types of tests are very heavy on conditional operations, which are not very good to use in shaders. So that's often very expensive. But it can actually be very cheap, too. If you take actually just the min and the max values of your colors, it provides a pretty good representation in most cases. It's not perfect all the time, but it's really cheap to do, and it gives some pretty good results. There are some caveats to doing it. There are some artifacts, which I will show you later, that can arise. But it's worked out pretty well. So once you've got your endpoints through your min and max, you have to start building your binary color values. Now, on a GPU, especially with Shader Model 3.0, there are no bitwise operations that you would typically use for doing shifting and masking and things like that. Not really that hard to deal with, though. You can replace these with arithmetic operations. So here I'm taking the minimum color, simply multiplying it by 255 to get it into an integer range. I'm using a divide by 8, 4, and 8. That is essentially just truncating the lowest bits, so you wind up with a 5-bit, 6-bit, and 5-bit ranged value. And then I'm using a dot product to take that value and multiply it by a couple constants. Now, what this is doing is it's shifting each of those colors over and adding them together. So at the end, you get a color value that is a 16-bit unsigned value. Excuse me. And then again, of course, you want to do that for your second color. Using the int here, int3, simply truncates off some fractional portions. It's not supported on all shader models. I believe the PS3 doesn't support it, but you can just floor the results instead of using ints. Okay, so even though this particular implementation doesn't support the DXT1 alpha mode, you have to still account for its presence. DXT1 alpha mode basically is triggered when your color 0 is less than or equal to your color 1 value. So you generally don't, unless you need to use 1-bit alpha, you don't want to let that into your shader. So there's two cases that you're going to want to test for. The first is when your two color endpoints that you've calculated, now as 16-bit values, are identical. Basically what we can determine at this point right now is that all the pixels in your block are the same color. Normally, if you just output this data, it will turn it into the alpha mode, and you don't want to do that. So what you can do is take those colors, simply add 1 to one of the colors, to the first color, and here you can hard code your indices to a known value. In this case, I'm hard coding all of the indices to use the color 1. So at this point, I can return from my shader, early out, and we're done. And this actually is a great optimization for the algorithm because a lot of textures have a lot of flat areas where you only have one color for a block of pixels, and it can cut out half of the operations of your shader. In the case where they're not equal, which is almost any other thing but a flat area, you have to just compare the two color values, and if the first color, color 0 is less than color 1, you're going to simply swap your endpoints. And so you swap your min and your max color. So once we've gotten our colors there, we need to find which indices you want to use for each of your texels. The first thing we're going to do is create a line that represents the line through color space. So you take your two endpoints, subtract them, and normalize that value. Once you have that line, you can go through each of the texels, and you can project each of the texels onto that line. Now, given that projection, you can determine how far along between your first and your last color on that line each texel is. Once you've got that relative distance along the line, you can compare it to a set of values. So the operation there is comparing to give me essentially a bit field of am I greater than the first, am I greater than the second, the third, and the fourth stored colors. Once you've got that comparison, you can take the result and use a dot product to multiply it with some constants that I have here. Now, the result of that dot product is it can give you the actual index that you want to use for that texel. It's a quick way of doing it, works really well. And once you've got that index, all you have to do is bit shift it over and add it to your indices. Now, this loop right here is for 8 of the texels, storing in index x. You'd want to repeat it again for the next 8 texels, and they'll store in the indices y variable. At this point, we've got our color already in a 565 format, and we've got our indices, so we just have to store them in a block, store them in an output variable. Now, the red component will be the maximum of the two colors. The green component will be the minimum of the two colors, and you just copy your indices over. So before I go into a little bit more detail about what you have to do per platform, I'm sure you guys want to see a little bit of this. I know I've been a little light on images. So this is from a sample application that we put for the 360. In the center is our source image uncompressed. In the back left is a same image compressed offline. And on the right is the image compressed in real time. In this case, it's a 1024 by 1024 diffuse map, and it compresses in about 5.7 milliseconds. Now, just looking at it, you really can't see much of a variance at all. This is the actual variance between the textures. On the left is the difference between the offline compressed and the source, and on the right is the difference between the real-time compressed, GPU compressed, and the source. Again, not a noticeable difference. I can magnify that. This is the difference times 10. So you do see that there is a quality trade-off between doing it offline and doing it at runtime. However, the trade-off isn't that big. If you are just looking at it without magnifying it, it's not very noticeable. Okay, so back to what you have to do per platform. starting with DirectX 10.1, because that's actually the easiest platform to work with. In DirectX 10.1, they updated their copy resource function to allow you to copy from a 16-bit render target straight into a BC1 or DXT1 texture. So all you have to do is render to a 16-bit fixed point render target. Again, this could be 1/4 by 1/4 of the resolution. The DXGI format, R16, G16, B16, A16 uint works very well there. And use copy resource to copy the render target to the BC1 texture. Very simple. Unfortunately, this doesn't work on DirectX 10.0 because it simply does not support copying between 16-bit uint targets and BC1. Xbox 360 has two methods that we've tried that work pretty well. The first one that we use is very similar to DirectX 10.1. You render to your 16, 16, 16 target, and then you can resolve that to a 16, 16, 16 texture in main memory. When you do that, you create a second DXT1 texture that shares the same memory with your 16, 16, 16 target, and voila, you have your DXT1 data. On the 360, it's very easy to share memory between textures. You can specify where the buffer for that texture is. The second method, which is actually the one that we wound up using across the board, is using memexport to write to memory directly from the shader. The reasons that we went with this method are twofold. First off, it doesn't require that we're actually writing anything to EDRAM. You can turn off color writes while you're doing the compression, and you're not polluting anything in EDRAM. And the way our render frame was set up, that was beneficial for us. We wanted to keep some stuff in there. The second thing that was a major benefit to us is that it saved us about 100 microseconds in the process. Having to do the compression followed by a resolve, you have to do the resolve after your compression. By writing out while you're doing it, you're essentially parallelizing those two things. Using memexport, it is slightly harder to use a tiled or a standard DXT1 texture. We wound up going with DXT1 linear textures across the board, although you can do the tiling calculations in your shader if you would like. And if anybody's interested in that, you can speak with me afterwards. PS3 was the most difficult platform to work with for this. PS3 lacks a 16, 16, 16, 16 fixed point format texture. At first, we weren't even sure if we were going to be able to do this on the PS3, and we had considered doing other things using the SPUs and things like that. What we did come up with, though, what we did come up with was we could use a 16/16 texture instead. What we do is instead of going with the 1/4 by 1/4 resolution, we go with 1/2 by 1/4 resolution. So for a 1024 by 1024, we use a 512 by 256 target. In the shader, we detect whether we're writing to an even or odd pixel, and we alternate writing the colors and the indices. So for one, we'll write out a color block for one texel, and the next target texel over, we will write out the indices for that. There is about a 25% cost overhead for doing this because you are doing some of the work twice. Essentially, for the color block, you only have to find the colors, but then for the next one over with the indices, you have to find the colors, go through that whole process again, and then also find the indices. So there's an overhead for doing it. So once you've got everything working, it's worth noting that you should really take a look at the performance of your shaders while doing this. Shader compilers are smart. They keep getting smarter, but they're not perfect. When I first implemented this on the 360, the shader compiler was giving me a shader that was taking about 2 milliseconds to run. By simply instructing the compiler to unroll some loops versus looping it, it cut it down to 0.5 milliseconds. So it was about a 4x difference in cost just by using identical code with an extra tag in your shader to tell it to unroll. The compiler now does a lot better job. Kudos to Microsoft on improving that. But you don't know what the compilers are across platforms. You should always just make sure you're taking a look at things like that. The second thing that you can do to help performance is creating specialized shaders for dealing with different formats. We use CTX1 textures for normal maps on the 360, which is only going to store 2 components per normal. Well, when you've got 2 components instead of 3 for all of your color values, there's actually some nice things you can do. You can store 2 colors in every register. When you do that, a lot of the map becomes parallelizable. You can operate on 2 pixels at once instead of 1 pixel at a time. So it cuts out a significant number of instructions and registers in your shaders. Alone, that would give us, a nice performance win. The thing is, normal maps using the min-max don't compress really well. There's an artifact that when you use min-max, you can essentially represent 1 gradient from bottom left to top right. And in normal maps, you really want to be able to pick at least 2 different gradients for a block. 1 gradient this way and another going from bottom right to top left. So in our normal map shader, we took our savings that we have on instructions and modified how we generate our colors, or how we pick our endpoints, to do additional testing to see which one of those gradients is the best one to use. So for our normal map compression, again, we've got our source in the middle and the offline and real-time behind it. You can see, again, the variance is, even with the additional optimizations, is a little bit higher on normal maps. It hasn't really proven perceptible. When you magnify it, again, you get additional artifacts in the real time, similar to the artifacts you see offline, though. Certain things, especially normal maps, just tend to not compress well with DXT. So this is a video that I took running on a 360. Here we are rendering a scene, resolving it immediately, compressing it, and redrawing it over there. And on the right, you see a little bit of a magnification of that. This is really just to show how this is all being done within the scope of 1 frame here. You can see the compression looks pretty good here. There's some banding artifacts because you're going from a 8-bit per channel color to a 565 color. But it's overall pretty good. Now, in this next slide, by simply changing the colors that are on the teapot, you can see on there already that you're getting a lot of artifacts along the edge. This is a result of using min and max for colors. When you're using a min and max, let's say you've got a red and a green as your 2 primary colors that are in your texels. Well, your min values are going to be 0, 0, 0, because the min of red and green is 0, 0, 0. Your max is going to be 255 red, 255 green. So your endpoints aren't going to represent either of the colors that you want very well. If you're going to have a lot of textures that are falling into this case, it might be worth spending a little bit more time on how you compute your endpoints. The paper from Intel provides some other alternatives that worked out very well. We found that when compressing textures, though, we weren't running into that case very much. This is an exaggerated case, and so we weren't running into that much. It wasn't worth spending the extra time. So actually, that is all that I had to say. Are there any questions? No? Okay. Well, if you could fill out the evaluation cards, it would be much appreciated. And if anybody does have any further questions, you can feel free to email me with them.